Okay, so the b over 2 squared part is the worst step normally. So here my b is 8. So 8 over 2 is 4, and 4 squared is 16. So what we're saying is we're going to add 16 to both sides. Is everybody okay with that? That's what we're adding. So that's step 3. Step 1 and 2 were already done for us, right? How nice of him to set us up so lovely. Okay, did everybody get that that's x plus 4 squared? Okay, a little hint, by the way, if you're not sure what number should go in here, rather than having to refactor this all out and make sure it's a perfect square, it's always, and I don't say that often, you know, but it's always going to be whatever you squared and added in. Okay, so we did 8 over 2, that was 4. 4 squared is how we got the 16, so it's going to be the 4 right here. Okay, so it's just a little shortcut if you don't want to have to do that. Okay, so what I've got is x plus 4 squared equals 25. So I've gotten the left-hand side written as a perfect square. And now take the square root of both sides. Did everybody do that already? Y'all rock. It should fall out on the left-hand side, just whatever was in the parentheses, right? And that's going to be equal to only the positive on the other side, which is 5. X plus 4 equals 5. Again, look how nicely he set that up for me so that I don't have to do weird stuff. Square root of 25 is perfect, right? And then subtract 4. Did everybody get a 1? Check my arithmetic. Yay. Alright, so that's one of those nice, lovely ones that's already kind of pre-set up for me and everything looks great and la-la-la-la. Nice. Okay. You can see how with these it would be pretty easy to do this one geometrically, I think, because you would just go x squared, 1, 2, 3, 4, 1, 2, 3, 4, and so it would be x plus 4 and x plus 4, and then you just got to figure out what goes in the box to make it a perfect square, and that's going to be a what? 4 times 4 gives me 16, right? Okay, so you can see how these are actually, the way they're set up. Somebody said earlier, I think it was Darby said, it's even. You notice these are even numbers, right? So in now modern days, all of our completing the squares aren't nice and pretty. We're going to do one in a second. Okay, they're not nice and pretty like this, right? But the ones that are set up to be able to geometrically complete the square, they need to be even numbers so that I can go 4 and 4. Because what if it was 9x? It'd be x plus 5 times x plus 4, right? And that's not a perfect square. So nothing from here down will work if it's not something that I can do nicely. Now later, whenever we really started getting into the algebra and stuff, we realized, oh, they don't have to be even numbers. We can just say 9 divided by 2 and make it a fraction, right? But he's not going to be messing with fractions, okay? You're like, no, 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 okay? So these are all going to be nice, pretty numbers. All right. Just to make sure everybody can do it, here's your one, and I'm not going to say a word. I'll just let you do it. It's going to be so much fun. Here's one where you have to use all 6 steps in modern day stuff. So 3x squared, so solve for x by completing the square. Okay, 3x squared plus 12x minus 27 equals 0. Dr. Webster's not near as nice as Al-Khwarizmi. You have to do all the steps.
Already messed
Uh-oh. We'll talk about it in a second. And this is our nice modern day problem, so you'll notice that I threw in the plus or minus. So mean of me. If you didn't put the plus or minus, it's okay, I understand. We haven't been working with them, but nowadays, when we give a question like this to our current day students, they need to know the plus or the minus, right? All right, so if you're still working on it, I'm just going to make sure we've got it. 3x squared plus 12x minus 27 equals 0. I see that a equals a 3, and the first step is make a be equal to 1. So I divided everything by 3 all the way across so that I get a leading coefficient of 1, right? That's what I'm after. So that gives me x squared minus, or plus 4x minus 9 equals 0. And then step 2 is move the constant over. So I've got x squared plus 4x equals 9. Are we okay there?
Skip the first one.
See, I told you, you gotta do all of them. Yeah, so, and it really does make a difference whether there's a 1 out there or not, because otherwise, am I gonna get a picture like this if it's 3x squared? No, it's gonna be like 3 big x squares, right? So it's not gonna work out the same. So it's gotta be 1x squared out there, that's why.
I forgot the first step.
Yeah, gotta go back and catch it, right? Okay. So, because I'm not as nice as Al-Khwarizmi, I told y'all that. I warned you. Okay, step 3 is take your b, which for us is a 4 now that I've got this guy, right? Take your b, divide by 2, and square it. Well, that's 2 squared, or 4. Okay, so I'm adding 4 to both sides. X squared plus 4x plus 4, if you don't, you can factor that, but I said it's always, don't use that always word much, but it's always going to be whatever I ended up squaring, right? X plus 2 squared. Equals, and of course I can't be nice to you. I was nice and made this be an even number, so you could take half of it and not have a crazy fraction in there, right? So this equals 13. When I square root that, that is not pretty. Square root of 13 is not a nice number. Plus or minus, because we put in the square root, right? And then the last step will be to subtract 2 from both sides, but unfortunately, because I have the square root of 13, I can't do much with that, right? So it's just negative 2 plus or minus the square root of 13. So this is the kind of question we have taken Al-Khwarizmi's little geometry thing to and just warped it and made them do all kinds of stuff, and here we go. So this is the modern day completing the square. That's how we do it nowadays. That's what you would see. And that's what you'll see in your middle school classrooms as you're working through some pre-algebra, algebra kind of stuff. All right? Okay, the cool thing about this for Al-Khwarizmi is this totally opens up the door for solving quadratic equations, right? We haven't done that really in the past. We've used Pythagorean theorem a little bit, but we haven't done something where it's just like solve for one of these things, you know, at x squared. So that's where we're going to take that as we work our way through history, solving quadratics. There's this guy, Al-Khwarizmi. And by the way, you asked me how you say his name. I've also noticed if you look in different texts or you look him up online or something like that, it's not always spelled the same either, but it's the same guy. So just like, sometimes they don't put the H in Khwarizmi, they just say KW. So, and sometimes I've seen a Z as an S, Khwarizmi instead of Khwarizmi. So if you see something that's pretty dang close to that, it's probably him. It just depends on, probably it's a translation issue would be my guess, between the Arab and...
The Britannica has a line over the A in Khwarizmi in the left eye.
Has a what? A line here?
No, on the A, on that A.
That's an O, but
Well,
for me it's an O, but it depends on, like I said, depends on your
They
tree.
have it as an A on Britannica and all the other.
And an I with a bar over it also. Yeah, so that's going to be something dealing with the phonetics of the Arab would be my guess.
And the Britannica website.
Okay.
Britannica's pretty good
Yay.
to go to.
Good resource. Okay, so he is the one that solved the quadratic, and then he started, that opened us up for all types of problems. Generalizing of problems. So that's what you'll see happening, like somebody will say, okay, solve all these quadratics. And nowadays we say, and you guys were right, whenever we look at those, we think, oh, a quadratic, if I graph a bunch of points that are solutions to quadratic equations, that gives me a parabola, right? So we kind of put those in families. It's what we call those. Okay, everything that's a quadratic, a parabola, those are in the same family. If you're an absolute value, you're in the same family. If you're a cubic, you're in the same family. So we start putting things together and generalizing. Oh, if you're a quadratic, you can solve them. And by the way, you can solve any quadratic by using completing the square. It might be time consuming and you might get ugly numbers like square roots of weird numbers or fractions, but it's still solvable using completing the square, which is yuck. Okay, sometimes it's just, takes forever. All right, just always quadratic algorithmic sometimes goes and only does algebra. Shh. It's amazing. So this is the first guy. Okay, later his books are translated into Latin. And we like that because Latin is kind of the scholarly language, right? Everything that we do, we have kind of a Latin-based language, so whenever we see that, it's good. His book, Algebra, turns in, with the algorithmy, turns into Liber Algorithmi, and it will be spelled differently than he spelled it, and that's because it's the Latin. You can thank probably some of those priests or monks or whatever who were copying things down and changing them into scholarly languages, okay, where Liber means what? Book, right? Okay, so the book of algorithms is basically what this means, okay? And so that's him. He also ends up with a book called The Book of the Form of the Earth. And that's the one where he actually gives like listings for longitude and latitude for different places on Earth. Okay, so that's kind of a cool thing that he did. Yeah. So it's kind of interesting. He was involved in trying to figure out what 1 degree would be in longitude and latitude, like the meridian. They were way off. Okay, just FYI. It's one of those epic fails in math, but at least they were trying to do that kind of stuff, so that's kind of cool. He had another book that was called Liber Quatrains, which means the book of squares, quatch, right? Quadratic, book of squares. And he spent a lot of time in there talking about all these solutions for quadratics and x squares and Pythagorean triples and things like that. So those Pythagorean triples come in. He's really responsible for a lot of notation. So even though you may have never heard of algorithmy before, you can thank him for modern algebra. Okay, he's the one. All right. Real quickly, let's get the other guy in. We're not going to spend time on him, really. But his name is Omar Khayyam. Khayyam. Omar Khayyam. He is 1,048 to 1,123. So, hey, we're getting almost modern here. That's 1,000 years AD. Okay, he's in the area that's Iran today. So again, kind of on that Arabian Peninsula where Iraq and Baghdad and all that are, right? Okay, he's in Iran today. Not back then, it wasn't that. The kind of cool thing was that he was around whenever the Turks decided that they were going to overthrow Constantinople, and so this kind of turns into a big religious war. It actually leads to the Christian Crusades, and we'll talk about that after spring break. So it'll lead us up to that Crusades time when people are just, crazy fighting and stuff like that. His cool contributions are in the calendar. Okay, going back to day one here when we talked about calendar, he had noticed that the calendar was shifting. Okay, it wasn't always that the 15th of March is the Ides of March, is when there's a certain kind of moon, right? Sometimes it might be the 16th, 17th, 18th, 19th. It's shifting, and he was like, oh, it shouldn't be shifting. The Ides of March should always be the Ides of March, right? So he actually came up with the idea of leap year. You can blame him. And what he said is there will be 8, it's actually kind of weird, 8 leap years for every 33 years. Okay, so that's, if you'll notice, that's not quite 1 and 4, right? This gives us that whole thing. Have you heard, there's not really 365 days in a year, right? It's 365 and a 4th days, right? Which is weird, we never call it that. And that's that leap year that goes in there that gives us that 4th day on average. Okay, so every 33 years, he said we're gonna add a day, basically. Okay, he came up with something that was called the scientific method. I'm almost done, guys, I promise. You're not gonna see me on Thursday. He refers to Euclid and Apollonius's conics. I just want to be done with the... Okay, so he does a lot of looking back at works that's already been done. And the cool thing that he's known for is that he was the first to solve the cubic equation. So this is his big first to solve cubic equations.
What does this mean, like Pauline?
What?
Refers to Euclid and what?
Apollonius, Apollonius. Apollonius. He was the guy that wrote the conics. He was a Greek guy. Both of these were Greek guys, right? Okay, and they're listed somewhere in our Greek section. Okay, so he did a lot of looking back and talking to them, but he was the first to solve the cubic. So if you can say Al-Khwarizmi was the first who kind of opened up quadratics for us, cubic, that's y equals x cubed, right? So think about if it's in some weird format, which later we'll talk about in Europe, how they solve the cubics in multiple different ways, so we'll spend some time with that. But he's the first one, and what he did was he solved it geometrically. So that means not algebraic, no algebra. And the problem with his, or the limitation, I'll say, for his, is that he was all non-negative. Okay, so that's his big claim to fame. All right, and that's it for Omar Khayyam. Omar Khayyam. You have a homework that I added. If you came in late, I'm afraid I'm about to lose Gilberto. So Gilberto, you good? You got 2 minutes? Okay. So if it cuts out, I'm sorry. Have a good spring break. I won't see you Thursday. Alright. So that's the end of the Arabs. And when we come back from spring break, we're going to be looking at Europe. If you came in late, here was the new homework. All due after spring break. Okay, so the only thing that is due between now and spring break is the project. Yes, you have to get me the project on your area. I won't see you before spring break, so be safe. Nobody come back with any broken arms or broken legs. I don't like that. Okay, I've had people that did that before, skiing on spring break. So be safe, be safe, be safe. All right. And you, Miss Kayla, I hope your spring break's going well right now.